down here by the River Thames, and you might notice that my voice sounds quite normal, yeah, and we've learnt that sound travels in waves and by vibrations through the air, and it travels slower than light, the speed of light, because we've done light, and it reflects and it refracts, a little bit like light, but it's sound this time. And so I'm here, and in a minute I'm going to go into the Greenwich Foot Tunnel. All right, so I just turn round, and then we've got, so that's the Greenwich Foot Tunnel on the south side. Remember Oliver Twist, we did the south side of the Thames and the north side. Yeah, so this is on the south side. And then if I turn it around, whoops, don't want to make you dizzy, like over there, just see there, that is the north side of the foot tunnel. So I'm going to be right underneath the river. So I'm going to go down the steps with my bike, and I'll be down just about in the middle of the river. And I want you to make a prediction about if you think my voice might change, or the sound of my voice might change, or the sounds down there might sound different than they do when I'm just here kind of in the open air. Another thing I was going to add is what do you think happens in space? Because we know that on Earth sound travels through the air, but in space there isn't any air, so would sound be travelling around? Would someone hear you scream or laugh? Hello! You can hear an echo. I'm in Greenwich Foot Tunnel, and I think you've got a couple of PowerPoints on sound. And I just thought I'd tell you a bit about echoes. I think this week we could design our own ears, and also talk about frequency, decibels, and a bit more about pitch. So have you ever wondered why the wind whistles? And we quite often, when we're doing our writing, we have the wind whistled or the wind whooshed. And it makes that sound because it's created by pressure waves. And as the air rushes past, branches and leaves, and these really long grasses are a good example, the pressure of the air makes that whooshing and whistling sound. Hi. So I'm down here by the Thames on the beach, and the tide is out, and it got me thinking about sound, and also how we measure the depth of water. And you might know about something called sonar, and sonar is something that submarines use to measure how shallow or how deep the water is. What they do is they have a machine, and they send out sound waves, and that sends an echo back. And if the echo comes back quickly, it means that the water isn't very deep, might be quite shallow. And if it takes a much longer time for those sound waves to come back, then that means that it's deeper, okay? And you can imagine how difficult it is measuring sort of how deep the Pacific Ocean is. Bats can see with their ears. All of the tunnel is very hard material, and it's a little bit like a cave. And remember I told you about sound, it travels in vibrations and waves. And that sound is hitting the hard surface, and it is being reflected back, all around this tunnel. When you've got a shell and you listen to a shell, lots of people say that they can hear the sea in a shell. And when I talk, when I hold a shell to my ear, I can hear my voice differently. It's really funny. And that is because inside the shell is a great amplifier, okay? Because the air gets wrapped around, and so it really resonates in the shell. And it's just air resonating that makes you think that it's the sound of the sea. But I would try that. Listen to a shell. and also talk or maybe even sing a song, because your voice sounds really different through the shell, because it resonates and it amplifies it. So have you ever noticed how when an ambulance goes past you at high speed, the siren seems to go up and down in its pitch? Yeah, and it's the same with cars that go past you really quickly. It goes meow. Okay, so that's called a Doppler effect. First of all, I've got a buzzer from my kitchen that I use for timing things. And I just want you to listen to it. And it's just one sound, okay? And in a minute, I'm going to put it in a plastic bag in a minute and fling it around my head, and you're going to see a change in pitch. And that is basically the Doppler effect. Now I'm just going to demonstrate this. You don't need to do it at home because I don't want you swinging things around and breaking things like that. But I just want you to hear the change in pitch to show you what the Doppler effect is, which is the same, you know, when a car passes you at speed. So listen to this. Yeah, so as the buzzer moves away from your ear, there are fewer sound waves. And as the buzzer comes up to your ear, as it comes nearer to your ear, there are more sound waves. And that creates the Doppler effect. Right, last week we had a look at sound, and we had a look at amplitude, which was how loud or how soft a sound was. And we also had a look at pitch, which is how high or how low a sound is. I'm just going to explain to you a little bit about how pitch is measured. And I'm going to show you some sound waves later, or I might have shown them to you before. But what you want to imagine is so pitch is measured by frequency, all right, and it's the number of times something vibrates. You know those little shakes. You know, sound, it travels through the air. It travels in waves, in vibrations, and I've just got my earphone things. I just want to demonstrate. So the vibrations, they are measured in a unit called hertz. And hertz is just what people that work in sound use in order to measure the pitch, how high or how low pitch something is. It's a bit like centimetres and inches and kilometres and minutes and seconds. It's just a unit of measure. So hertz is used for measuring the frequency, the pitch of a sound. And it's the number of vibrations something makes. So imagine that is like a string on a guitar, or it's just a piece of string vibrating, okay? And I'm going to imagine that's really vibrating, yeah? And imagine it went at 20 vibrations a second. That would measure in hertz as 20 hertz. So it's the number of vibrations a second. Now, humans, we can hear between 20 hertz and 20,000 hertz. And then after 20,000 hertz, it becomes uncomfortable. The pitch is too high, and actually we just can't hear it. And below 20, when it comes below, we just can't hear those sounds. The pitch is too low. Interestingly, wind turbines, they've got, I don't know what hertz it is, but they're below 20 hertz. And we can't hear the sound of those big white turbines because the frequency of sound, the frequency is too low. The hertz measurement is too low for us to hear as humans. And there's a couple of species. There's a moth which can hear the highest sounds, and that is 300,000 hertz. Okay, moths is a certain species. I'll look it up later. And bats can hear at 200,000. And their use of echolocation is when the sound waves go out and the echo is reflected back, and that's how they use That's how they use their hearing to know where they are as they're flying around in the cave or in the darkness. This is an example of a quieter sound, and basically they measure the number from there up to there, and the lower the number, the quieter the sound is. Now this is an example of a louder amplitude, okay? And as you can see, the wave is much higher and then it dips right down, and that would be the measurement of a louder amplitude, okay? And now I'm going to sort of demonstrate how something is measured in decibels, and as I'm down here on the beach, I'm just going to see if there's a change in the sound of the rocks that I'm going to throw in the river. Got a small rock here, and I'm going to see what the sound is. Is it going to have a lot of amplitude or a smaller amount of amplitude? Right, I'm going to try another one now. A little bit bigger this time. Yeah. Right, I've got a really big rock here, and I'm going to see if it's louder and if it will measure more decibels. Yes. Now, the splash of the second rock was much louder, and loudness or amplitude is measured in decibels. Now, with pitch, remember that's about how high or low a sound is, and this is how we look at pitch when we want to draw the sound wave. And this is a low pitch sound, and this will have a smaller number, so we know it's a deep noise, low. And this is high pitch, and this shows a pitch that will have a higher sound. So, you know, that might be someone, squeaking or something like that. And this audiogram, it's got the frequency, the pitch, is on the horizontal. You know, we go along the corridor and up the stairs, yeah? And then up the stairs, we've got the volume, which is the decibels. And on here, you can have a look at the green bits show normal human hearing. So you can hear birds and rustling leaves and a tap dripping, okay? And then as you go through, if you see the red ones, if you can't hear those things, then you've got a problem with your hearing. It's quite interesting, that audiogram. And the little lines, it shows just the left ear and the right ear. Because when you have your hearing tested, they test both ears. I don't know, my class might have seen these, I got these for Christmas. These are my Hobbit ears, because I'm a bit of a Hobbit Lord of the Rings fan, and putting those on. I don't know whether these are going to improve my hearing. I'm looking at the design though. It makes them longer. I don't know whether that's going to affect how sound travels in and the vibrations. But I had a bit of an idea when I found these in class. And I thought maybe think about animals and insects and all those different species that you know, and think about their ears, and then design some ears that might be really good for hearing different frequencies. Now this animal, it has the biggest ears on Earth, and that I mean relative to its size, okay? And it's called a jerboa, and it comes from Mongolia, South Gobi Desert. But when you're designing your ears, I want you to think about things like horses and dogs and bats and moths and other unusual things that you might find on the internet. Dolphins are mammals that have exceptional hearing as well as great eyesight. They use echolocation to also hear underwater. Are your ears going to be fantastic at amplifying and hearing different pitches? Okay, what special quality are your ears going to have? Right, so I've had a little play and I have made some ears, and now, what do you think of those? Now, there is a problem with these ears because I haven't allowed a space to actually hear anything with. Now, remember, I don't want you poking things into your ears. Don't poke things in, that's really dangerous. But what you do want to do, you want to make sure that you really try your ears out. So this is quite a good way, and I can already hear a difference. The sound is quite muffled. Right, so I might then try a different design, like these ones. These are just an old paper plate, you can do it with card. So I'm going to try, kind of like the rabbit ears, and yeah, these are quite similar actually. It's definitely a muffled, more dull sound because I can only just hear the children playing in the playground. And now I can hear them much better. So you want to have a little play around with your ears. Now I just used 2 old paper plates, but you can just use card and, you know, cut the shape out. You know, it might be, if I fold this in half, you know, I might want to try out the cone in a different way, like that. Actually, that's quite good. So, you see, I'm not sticking anything in my ear. I'm just making a shape that covers it. Actually, these are good. These are good. Mind you, I'm not quite ready to give up my human ears yet. I went to work on the ears a bit more when I got home, and I've made this shape, and these are great for really directional sound, and they fit. They fit quite well actually. I shouldn't wear silly earrings like this. Look, like that, and they're quite funnelled, and these ones, this fits over here. And I've been experimenting with the angle, and I've also been experimenting with different sounds. So I've played myself some music, listened to the radio a bit, the telly. I've gone outside to see if I can hear any birds or, you know, things, or cats or foxes rustling around in the garden, and it is definitely a different experience. So do try your ears out and think about what they are good for. These ones are great for very directional sound.